All right, guys. So now let's look at refrigerators, air conditioners, and heat pumps. So we talked about heat engines. So the heat engines are devices that take the energy that naturally, spontaneously flows from hot reservoir to cold reservoir and uses some of that energy to convert it into useful work. Okay. That means the idea is that it always, uses the energy that naturally transfers from hot reservoir to cold reservoir, which is a natural direction. And heat engines is again, they're useful because we can always extract some of that energy into useful work. We saw that theoretically you can never have 100% heat engine, 100% efficiency. Most of the energy you can see, right, technically then ends up being dumped out. So um, there's a theoretical maximum efficiency that we can have, where in practice, if we try to build any heat engine, we can never go beyond that theoretical, we can never even reach that theoretical efficiency. And always we are about 60 to 80% of that theoretical efficiency. All right, so now here we're going to look at something kind of like a little bit different, sort of like a reverse of that. What if you want the energy to go from cold to hot rather than hot to cold? Well, one thing we know is that if we try to go from cold to hot, that's not the natural direction of heat energy transfer, right? That means on its own, spontaneously, heat will never go from cold to hot. In order for us to achieve that, we must put some energy into the device to perform this task. That means some work has to be done on the system in order for us to have energy flowing from cold to hot. All right, so we have such devices: heat pumps, refrigerators, air conditioners. Those are the devices that technically do that. So, and you can see right there, essentially heat engines operating in reverse. But, so one of the things we have though, one example, for example, let's say here, I give you the example here, is the air conditioners. So air conditioners transfer energy from cool room in home to a warm air outside. Okay. So, and this is a simple model of that. That means you have a cold reservoir at TC, T cold, or TL, T lower, right? Lower temperature. And we have energy go into a heat pump or, so like air conditioner, right? So the idea here is that in order for the heat to go from cold reservoir to hot reservoir, a work has to be done on the system in order for us to achieve that. Now, for example, if we talk about air conditioners, well, there's a lot of things going on in air conditioners. So let me sort of give you a very quick, overview of that. So generally, air conditioners transfer heat from indoors to the outdoors. Okay. So sometimes it feels like air conditioners actually creating a cool air and blowing into the room, but that's not the case, right? So you don't have air conditioner just creating a cold air and blowing into the air into your room, into the inside. That's not what happens. What happens here is that heat is actually removed from indoor air. And when you remove heat from indoor air, it cools down. Okay. So that means you can think of like this: the condition what you have here is that generally is that the heat is flowing from inside air into the outside. You're technically reusing the same air that you have inside. What you're having here is that you just removing the energy. Okay, so let's look at the cycle. Okay, so air conditioner pretty much uses the some of these laws that we learned. That means first law of thermodynamics and some of those Boyle's law, Charles law, Gould-Sachs law, where the pressure is, when pressure changes, temperature changes, when volume changes, pressure changes, all of those things. Because air conditioner pretty much uses all of those things to get your room basically cool, to cool down your room. So one thing we have is that in the air conditioner, there's always sort of like most of them come in sort of like just two units. One unit is inside the house, another unit is outside of the house. So, like let's say we call like air, a split system sometimes. So What you have is that inside your house, there is a unit, and the unit that inside your house have the what we call a refrigerant or coolant. And that coolant absorbs the heat from your home, and then eventually it pumps into outside. Okay, but outside there's another unit, so that means, you know, we they work together to extract heat from your, from air molecules in the room. So then inside unit sends it to the outside unit, and eventually the outside unit basically releases the heat. Okay, so let's see in terms of, let's say, what's happening. I give you like in terms of like a 4 steps that goes into this air conditioner. So step one, what you have is that inside, for the inside unit, what you have here, you have this, what we call coils, so that they have, air flows um, over the indoor coils. Um, which then, in order to absorb energy from the air nearby, it has to be very cold. Because remember, the idea is that inside your house, the temperature of the airs, right, is hot. So that's why you want to cool it down. So then you have this, these coils inside inside your house, right? This unit, and then any, all the air that nearby basically releases energy, or energy from the air molecules is absorbed by these coils. Why? Because the coils are extremely cold. So here, which are which contain, they're cold because they contain this cold refrigerant. So refrigerant. Okay, so they contain this extremely cold refrigerant. That means when the air flows over this coil, the heat goes from hot, warm air into the cool, coils, right? So that means the temperature decreases of the air nearby the coils, because the energy spontaneously will go from hot to cold. Okay, so that's why they're specifically designed to be very cold, so that it absorbs all the nearby energy from the nearby air molecules. Okay, so and sometimes it can decrease the temperature of the nearby air molecules, quite a lot, maybe like 10 degree, 20 degree, depending on, let's say, how different the temperature, between the coils and the air molecules. Now, from here is then, after the refrigerant absorbs this heat, um, it changes the, um, let's say, the state changes from a liquid to a vapor. Okay, so basically the refrigerant. So it changes from a liquid to a vapor. And this warmer refrigerant gas then gets transferred to the compressor. Okay, now let's look at the step two into going into the air conditioner. Now the warmer vaporized refrigerant gets compressed to hot temperature. Let's see why we need that, but let me write it down here. So warmer vaporized vaporized refrigerant gets compressed or pressurized to um, to a hot temperature. Okay. Now, the reason we do that, because as, let's say, when this refrigerant absorbs energy, well, it warms up, but still, you can think of like this. We're talking about maybe a summertime where outside air is still very hot. Maybe it's 100 degrees, 100-degree Fahrenheit outside. That means you want to make sure that your refrigerant is always higher temperature than the air outside. Okay, so that means this the compressor, right, which is, generally located outside of your house, that basically the outside unit. That means when this warmer vaporite refrigerant transferred into the outside unit, the compressor over there basically pressurizes it and increases the temperature. All right. So now you can think like this. You have a refrigerant that has an extremely high temperature, and you have air molecules outside your house that have hot temperature. But still, if your refrigerant has a higher temperature than outside, then heat will go from refrigerant to outside. Okay. That means, for example, if outside is 100 degrees Fahrenheit, if you make your refrigerant 120 degrees Fahrenheit, then spontaneously, naturally, the heat will flow from your so basically from the gas from this refrigerant to air molecules outside. Okay, that means the temperature of the refrigerant will drop, right? It will cool down. Okay. Now let's look at step 3. That means we are releasing heat to outside. Okay, that's remember that was one of the important, right? So basically releasing heat to outside. Okay, now step 3 will be once we have that the refrigerant, right? So basically, which keeps the air molecules. So it's still relatively warm. I mean, we were talking about 120 degree Fahrenheit of the refrigerant. Let's say vaporized gas compared to the outside. Even if it releases all its energy, well, the temperature is still going to be very warm. So we can say that's still very hot refrigerant. Then flows into condenser coils. Where it loses heat to outdoor air. So okay, so that's basically, so after it's compressed, then you know um, it goes through the coils, the condenser coils, where it then loses their energy to the outside air. And the last step will be, which let's call it step 4, this refrigerant from outdoor is moved inside to the inside unit, and then it's basically a cool down. It has to cool down again, so then the cycle can repeat, right? Because if you send that warm air, still relatively warm air, into the inside unit, you can actually add some heat into into your house rather than, let's say, remove. That means there's still another condenser that will cool down the refrigerant. Okay, the warm, let's say, refrigerant then goes from the outdoor unit to inside unit, basically to get cold. Okay, then once it's cold, then it sends to the this indoor coils, right? That means by the time it gets to the indoor coils, there's a compressor which compresses, and then basically it repeats the cycle. Okay, so that's kind of what we have. That means first we absorb energy from inside, then that warm, let's say, refrigerant, right, has to be even warmer, even hotter. Then we basically increase its temperature to a very high temperature. So then it's higher than outside temperature. So then it releases the energy. Then we cool it down and set it inside the house to repeat the cycle. All right, so that's kind of what we have for the air conditioners. Another one here is a refrigerator, which kind of does, a very similar thing. So for the refrigerators, then what we have here is the process is that you have another compressor motor, okay, which then basically the idea here is that to keep the inside the refrigerator cool. Okay, that means the inside the refrigerator must be kept cool. What it does here is then this compressor motor, right, um, forces the gas go through this high pressure, okay, right, high pressure exchanger. That's basically there's a condenser coils. So as it goes through those, then QH, right? So heat is basically released to outside. Okay, because as it's warms up, because you have a high pressure. Well, high pressure means that you have a high temperature, and then outside, room temperature, room air molecules are cooler, so then heat will go from hot to cold. That means what we have here is that as they go through here, outside of the refrigerator, generally in the back of the refrigerator, then let's say all the energy will be then released to environment because the gases are generally going to be hotter. So that means you compress them to high temperature and then send them through those to those coils, and they lose energy. After that, they go through inside. So there are other cooling coils. So we have cooling coils which are inside your refrigerator. So then as they go through that, then because then they're cold, all the any type of heat that you have inside your refrigerator will naturally flow from inside into these coils. That means then you can see, right, QL from inside into refrigerator to coils. That means all the food and everything, whatever energy that they have contain, will then naturally flow from inside the refrigerator into these coils. So then when they move through this coil, come back to the compressor again. The compressor will compress to high pressure. By high pressure, then it will mean that the energy, the temperature will increase, and then send again through this, high pressure coils, right, condenser coils, which then will release that energy into environment. That means what we have is just that, right? So you take energy from inside the refrigerator, then we have to do work, right? This motor does work in order to move the heat from inside the refrigerator into outside of the refrigerator. On its own, it will never go, but we have to, we can do a little bit of work in order to achieve that. That means without this compressor motor, you can never keep your refrigerator cool. That means, if the compressor motor breaks, then, basically either replace that or replace the refrigerator. Okay. Now, the idea here is for this heat pumps and refrigerators is that you want to do as little work as you possibly can. Okay, because you want to basically take the heat and from at the lower temperature and then move it to high temperature. Okay, and in the process to try to do as little work as you possibly can. Now, can we do such let's say a device, such engine that doesn't require any work? Well, as we talked about, it's pretty much impossible. And this we have a classical statement pretty much stating that it is impossible to construct a cyclical machine whose sole effect is to transfer energy continuously by heat from one object to another object at the higher temperature without the input of energy by work. That means something like this, where you have a energy absorbed by cold reservoir and then it dumped into hot reservoir. Such heat pump, let's say, is impossible to construct. You cannot have without any type of input energy by work. That means you have to input some kind of work in order for this process to happen. That means you cannot expect that naturally this happening on its own. So there's also another statement, which is Kelvin Planck statement. It is impossible to construct a heat engine that operating in a cycle produces no effect other than the input of energy by heat from a reservoir and the performance of an equal amount of work. Okay, so they technically, even though it seems like different things, right? But they pretty much represent the same statement. Okay, so you can write Clausius and Kelvin Planck statements of the second law of thermodynamics. And again, these are two different ways we can describe second law of thermodynamics, are pretty much equivalent in all respect. If one is false, so is the other one. That means we have to take both of them true in terms of describing the second law of thermodynamics. All right, so and this is the heat pump, which again pretty much uses the same process. So you have cold outside. The heat pump is basically during the winter, right? So you want to pump heat into the house, but obviously the house house is warmer, outside is colder. Energy naturally will not go from cold to hot, but we can have a heat pump, and there's electric motor that takes the energy, very similar to the sort of air conditioning. So take the energy from outside, and then does work, and sends out then the heat into the room. So then your um, inside your house basically warms up. Okay. Again, without the this electric motor, this heat pump will not operate, or this process will not go, because again, those two statements tell you that you can never, without doing work, right, achieve any of this, let's say engines. Now, one of the things we can do here is we can calculate what we call coefficient of performance, which is a number describing effectiveness of heat pump. So similar to thermal efficiency or for heat engines, like we calculate the efficiency, right? So it's a ratio of what you gain, which is energy transferred to or from reservoir, to what you give, which is the work input. That means the equation COP for cooling mode, it's an energy transferred at low temperature divided by the work done on heat pump. That means this is how much we, let's say, receive, and how much work we have to do in order to achieve, let's say, what we want. And there's also a COP for the heating mode, which is energy transferred at high temperature divided by the work done on heat pump. So you can see that in terms of we have coefficient of performance for those two modes, cooling mode or heating mode. And then, the problem will basically tell you what you're dealing with. Are you dealing with air conditioner? Are you dealing with a heat pump? And you should be able to sort of like, let's say, use that to, let's say, solve the problems for, COP, which is again, kind of like, you can see, right, it's a ratio. It's it's a ratio that basically has no units, because you have energy divided by energy. So you can then just calculate some kind of number, multiply that by 100, and basically get like, let's say, a percentage or a fraction. All right, so again, so here's kind of giving you the refrigerator performance is measured by coefficient. So this is just to show that there are few ways we can write that. So for example, for the cooling mode, right? So you have QL over W or QC over W, which then W, remember, is always the difference, QH minus QL. So that you can write it as QL over QH minus QL. And we also have what we call ideal refrigerator, which is then TL over TH minus TL. So you can also, write it in terms of the temperature rather than in terms of energy. All right, so let's look at then few examples here. So the certain refrigerator has a coefficient of performance of 5. When the refrigerator is running, its power output is 500 watts. A sample of water of mass 500 gram and the temperature to 20 degrees Celsius is placed in the freezer compartment. How long does it take to freeze the water to ice at 0 degrees Celsius? Assume all the other parts of the refrigerator stays at the same temperature and there is no leakage of energy from the exterior, so the operation of the refrigerator results only in energy being extracted from the water. All right, so for this example, we are given coefficient of performance, right? So we are given COP, which is 5. We're given power, which is 500 watts, which, remember, it just tells you how many joules each second you have. Then we're given the mass of the, so mass of water, sample water, and that's 500 grams. And we're given the temperature, initial temperature and the final temperature. Initial temperature is 20 degrees Celsius. Final temperature is 0 degrees Celsius. Okay. So using this, we can then calculate how long will it take for this to freeze to ice at 0 degrees Celsius. That means If you remember from the previous chapter, then um, when we looked at in terms of energy required to change the temperature, then melt, that means we can look at it in terms of the Q, which is energy, then will go into removing, let's say when you remove energy from water at 20 degrees Celsius, it can go all the way to until decreases temperature to 0 degrees Celsius. But then you also need to extract more energy for it to melt. That means our net or total energy will be Q1, and this will be the energy extracted from water to take it from from 20 to 0, plus Q2, and this will be then energy that will go into melting it. So that means this is going to be then M water, C water, delta T, then plus. So technically it's, it has to be minus because we're removing energy. So minus M water times then heat of fusion. Okay, so this will be in terms of the Q. Well, that's because if you remember, the power equation tells you that um, this is equals to the work done divided by over time, right? Work over time. So if I rearrange this equation, then what I will have here is that T is equals to then work over power. Okay. Now the work will then go into changing the heat. That means I can say that this is equals to, using the equation that we just learned, right? Where COP is equals to um, QC over work done. So then we can use this to rearrange where then work done is equals to QC over the COP. That means I can say it's QC over COP times, times power. Okay. All right. So from here, then I can say that my QC here is M water, C water delta T minus M water times heat of fusion, and divided by then COP times then the power. You pretty much have everything. So then we can write down. So technically I can factor out the mass to make it a little bit easier. So what I have here is 0.5 kilogram. We have to convert it into kilogram. Then times specific heat of water, which is 4186 joules per kilogram Kelvin, times change in temperature. So it's going to be 0 minus 20, so minus 20 degrees. Then minus heat of fusion, which is 3.3 times 10 to the 5 joules per kilogram. Okay. And that's divided by COP of 5, then times power, which is 500 watts. All right, so then if we calculate, the time is going to be then 83.3 seconds. So it's going to take a little over a minute for this to occur. Okay. All right, so let's look at one more example here. For this example, we have 1 liter of 20 degrees Celsius water is placed in a refrigerator. The refrigerator's motor must supply an extra 8 watts of power to chill the water to 5 degrees Celsius in 1 hour. What is the refrigerator's coefficient of performance? All right, so in terms of then what we have here is coefficient of performance is equals to QC over work done. Okay. Now we are given the work done, which is 8 watts. Okay. But we don't have QC yet. Okay. But we are given the volume, which is 1 liter. Okay. And we're given the temperature, the 20 degrees Celsius initially, then 5 degrees Celsius. Let's say we're given 20 degrees Celsius here and 5 degrees Celsius over there. So that means we're going to chill it to 5 degrees Celsius. And we're also given the time, right? 1 hour. So let's say T initial is 20 degrees Celsius, T final is equals to 5 degrees Celsius. Then the time, let's say delta T here is 1 hour. Can like write it like that. All right. So one thing we do here is we go and solve for QC. Well, QC will be this. So it equals to mass of water times specificity of water times delta T. Okay. Now, what we have here is mass is not given directly, but we're given the volume. And remember, I know that density of water is 1,000 kilogram per cubic meters. That means I can find the mass. Remember, mass over volume is density. Then mass is equal to the density times volume. That means here I can say that for the mass is density of water and volume of water times specificity of water, then times delta T. Now, if you remember, in these equations, we have to make sure that QC is always a positive quantity. Okay. Now, if I do this, 5 minus 20, well, I'm going to get a negative number, right? 5 minus 20 is negative 15. So what we do here is you can pretty much put an absolute value or just say all we want to know is just 20 minus 5. You can kind of do it like that because all we want to know is just amount of this energy. Okay, not necessarily if it's flowing out or in. Because if you do 5 minus 20, you're going to get negative number, and there's no such thing as if you put negative here, so no such thing as negative COP. Okay, so what we do here is just basically we write it down 20 minus 5 or just use absolute value for that. All right, so let's then calculate this. So then density is 1,000 kilogram per cubic meters. Then what I have here is 1 liter ends up being converted to 10 to the negative 3 cubic meters. So then the cubic meters cancel out. Then specific heat, specific heat for the for water, 4186 joules per kilogram Kelvin. So then kilograms cancel out, and then 15 degrees Celsius. That's basically my change in temperature. Okay, so if I calculate this, I'm going to get 6.285 times 10 to the 4 joules. Then I can come back and solve for COP, which will be QC 6.285 times 10 to the 4 joules divided by the work done. But one thing we have here is, so if I write this here is 8 watts. Remember, you can see from here this. If I write down this as 8 joules per second, right? So you can see, right, I can cancel the joules, but units don't work. I have like 1/2. So, well, because what I need to do here is I need to make sure that I'm talking about all the Q's, let's say QC in terms of joules per second, right? Then I divide this by 1 hour because we're looking at in terms of the delta T as well. So this becomes then, sorry, this that's the work done is not 8, that's a power, right? 8 watts. Sorry, where power is equals to work over time. Okay, that means for the work, so let's see if I put joules here. So for the work, I have to put power times time. That's why it's power times time, which then ends up being 8 joules per second, then times 1 hour, where 1 hour is 60 seconds. So then I can convert it into seconds so they can cancel out. Anyways, plugging in everything, I get 2.2. I could have calculated first in terms of how much energy I have in 1 hour and then divided by that. But pretty much the coefficient of performance is 2.2. You can also do it like this. All right. All right. So next we're going to talk about a new concept of entropy. But first, let's look at in terms of what we have learned so far. So we have zeroth law of thermodynamics. That involves the concept of temperature. Remember, in terms of two objects not exchanging energy between them means they have the same temperature. That means they reach thermal equilibrium. First law of thermodynamics involved concept of internal energy, and internal energy was the sum of uh, energy exchange and the work done, either on the system or by the system. Now, one thing we have is that internal energy and the temperature, if you remember, they were state variables. That means in a PV diagram, so if I have, here state one, so I can calculate the temperature for that state one, and I can calculate internal energy for that state one. In a way, if I know the temperature, I know the state, internal energy. There's another way of calculating change in internal energy, right? But internal energy, remember, would only change if the temperature change. So the idea is that just internal energy is proportional to the temperature of one state. Then if you change this, you change that. And only change in temperature would theoretically change, the internal energy. Now, one thing important about those two, that they're state variables, which means their value as we go from state one to state two, their value is independent of the path taken from state one to state two. That means if there's a change in temperature, this is based on only the difference between temperature one and temperature two, regardless of if we got from one to two like this, like that, like this, or like that, doesn't really matter. So it's path independent. Okay. So obviously then some of those microscopic state variables that we learned, they are path independent, right? So, let's say pressure, volume, the temperature, internal energy, those are state variables, and they do not, depend on the path taken. But there are obviously other quantities that we also talked about that depend on the path taken, like heat and work done. Now, one thing we have here is then entropy is another state variable. Okay, another state variable, and it's related to the second law. And it's a state variable means that it's path independent. That means I can look at entropy at state one, entropy at state two, and see how entropy would change if we go from one to two. Okay. Now, one of the things we have about entropy is that when it was initially developed, it was just developed as a, sort of like a state variable, just like, other state variables that we have, just to allow us to, calculate certain information about our system. Later in 19th century, the statistical mechanics became very important in, let's say, calculating the behavior of substances at the microscopic level of the atoms and molecules. And as the statistical mechanics has developed and its importance became very obvious to scientists, then entropy actually started growing in terms of its importance, because entropy can be used to describe some of that information about microscopic or macroscopic, let's say entities like atoms, molecules, and it's related also to in terms of the we're going to see in terms of temperature. That means one of the things we have here is that we can look at it, entropy, and interpret the entropy from the what we call microstates or macrostates. So let's look at definition of those two things. So microstate is a particular configuration of individual constituents of the system, right? And macrostate, description of the system conditions from macroscopic point of view. Okay. For a given macrostate, a number of microstates are possible. All right, so let's look at in terms of what do we mean by those. So I'm going to give you several examples. And here's one example. Imagine you have let's say, a dice. So we're going to look at it in terms of this. Okay. So you have a microstate of six-sided dice, and you want to see what is the probability, right, for us to have um, basically a 4. That means when you roll this dice, you have two six-sided dice. When you roll them, What is the probability of having four? Okay. Now, to have four, then we can have one of them one, the other one three, or we can have both two, two and two gives you four, or then the first one three and the second one one. That means we have, let's say different ways we can get four, right? So we can have one three, two two, or three one. So how do we compare that to another microstate of, for example, two? Okay, for that, the microstate is just one. In order to get two, remember we talk about the dice, right? So we have a pair of dice. In order to get two, we can only have when the first one is one and the second one is one. That's basically two. That's the only way we can have. That means this, let's say having only one microstate possible, that means only when the dice are one and one, that's a microstate. The macrostate is basically having two. Same way, you know, getting four is a macrostate, and there are multiple microstates that can give us that. 3 1, 1 3, and 2 2. That means those are the microstates, but then getting the four is the macrostate. Okay. Now, what we have here, we can break it down into sort of like, let's say, into sort of like three important parts. So we have the uncertainty. Okay. That means if we know that microstate 4 exists, then some uncertainty as to microstate that exists. Now, what we have here is if you're comparing the uncertainty for getting 4 compared to getting 2, there's a lower uncertainty for microstate of 2. Okay. So then we have choice. So more choices of microstates for a 4 than for a 2. Then probability. So for probability, what we have is that microstates of 4 has a higher probability than microstates of 2. Okay, because there are more ways, more microstates for achieving a 2. That means imagine you rolling like, some n number of times. Obviously, getting 4, you have higher probability of getting 4 than getting 2, because there are, 3 different ways you can get 4, right? And only one way you can get, 2. So that's why you have a higher probability of getting 4 than getting 2, and there's a lower uncertainty, right, for the uh, for the macro state of 2. By lower uncertainty means that there's only one, right? There's uncertainty in terms of, is it going to be, for example, the uncertainty for the 4 is that when we get 4, is this first one 3, second one 1, or 2 2, or the first one 3, second one 1? So that means there's an uncertainty in terms of which one of those can give us 4. So, but in terms of the uncertainty for the macro state of 2, there's only one thing we can have. The only way we can get 2 is if it's 1 1. That means there's zero uncertainty. Okay. That means, uncertainty, choice, and probability. Those are the important factors when we're considering the statistical mechanics. Okay. Here's another example. We have a 5-card poker hand. So you have, two macro states. Okay. So one of them is a worthless card. The other one is a royal flush. Okay. Or 5 spades. So here's the royal flush, and this is the some kind of worthless hand. That means just pretty much anything. And one thing we have is that only one microstate associated with the macro state of a royal flush. That means royal flush is 5 spades, and that's it. Just like the when you're talking about in terms of getting 2, right, with your dice. There's 1 1 gives you 2 and nothing else. And then here only this, this specific, set of cards gives you a royal, flush. Where the macro state where we have a worthless hand, right? Well, you can have, pretty much any combination of cards giving you that. Okay. So that means every, let's say you get a particular hand, the microstate in each hand shown equally probable. That means what we have here is just any just wordless combination becomes a microstate of this wordless hand. Okay, so that's kind of like, let's say, in terms of what we have. Then you can again break it down in terms of uncertainty, right? Choice and probability, or is the probability of getting, a royal flush compared to the probability of getting, let's say, just a worthless hand. Now, the reason we talked about that is because entropy, which we represent a capital S, represents a level of uncertainty, choice, and probability in a system. Okay. Here's one more way to look at it. Let's say your system, because when we talk about, let's say, thermodynamic systems dealing with ideal gas or something like that, right? So that means we're going to see that we're dealing with not just, let's say, small microstates, but something like extremely large. And I can show you kind of like in terms of over here what we have. Consider container where we have mixture of oxygen molecules and nitrogen. Let's talk about having a container with one molecule. Okay, so we can break down container into two parts. Let's say the left side and the right side. So now, one molecule in a container has a 1 in 2 chance of being on the left side. Okay, that means we can say that as a result of random motion, right? It either can be to the left, on the left side, or on the right side. So I can write down the probability as 1/2, right? So basically 1 in 2. If you're then considering two molecules, being on the left side, then that basically becomes 1/2 squared. That means for both of those, if you have two molecules and having both of them on the left side, or technically both of them on the right side, then it's 1/2 squared, or basically 1 in 4. The probability of having that. Okay. Now then the probability of having 3 molecules in the container and having all 3 in one end, the left side, or 3 on the right side, becomes 1/2 cubed. Okay. Which basically gives you 1 in 8 chance, right? Probability is 1 in 8. That means that you can see, right? So there's sort of like a pattern, right? So this is sort of like a 1/2 1, 1/2 2 if you have two particles, 1/2 3 if there are three particles. Then let's say, for example, we have 100, independently moving molecules. Then what is the probability of having all 100, let's say in one end or the other one, or let's say out of the 100, probability that, for example, 50 oxygen molecules to be, so let's say we have 100, having exactly 50 on one end or the other end, then will be then 1/2 50. That means I want 50 oxygen molecules, for example, to be one end. Imagine if you have a room, right? If you have a room where there's a oxygen and nitrogen, and I want, oxygen to be on the left side, nitrogen to be on the right side. So then how can we have that in terms of what is the probability of that happening? Obviously, probably is much lower than having the oxygen and molecule uniformly spread around in the room. Okay. That means, for example, then if you're considering that room in terms of what is the probability of having, in terms of half of the room have just oxygen, half of the room just nitrogen, and assuming, let's say, in the room you have 100 molecules. Obviously we don't, but let's say if we have, probability of having, let's say here's your room, half of them, 50 of them to be here on the left side is just 1/2 50. Then other half to be just, let's say, put it like this, right? Other half to be then the nitrogen is another 1/2 50. which means then probability of having this macro state, that means like having on the left side just oxygen, on the right side just nitrogen, then we multiply this together and we get 1/2, you know, to 100. Okay, so that's kind of, what we'll end up getting if we are assuming this, okay, this result. So now what I have here is, you can see, right, if I thinking like this, so then it's 1/2 times 1/2, 50 times 1/2, 50 equals 1/2, 100. So it's 1 in 10 to the 30. That means the probability of finding this particular, system where half of it on the left side is all oxygen, on the right side is all nitrogen, like 50 and 50, right, is 1 in 10, 30, 10 to the 30. Now imagine, obviously we don't have 100 molecules in one room. We have several Avogadro number of molecules. Remember, Avogadro is 10 to the 23. Imagine then what extremely large, improbable, let's say probability we will have. What is the probability of having an Avogadro number of molecules and having all the oxygen to be on the left side, all the nitrogen to be on the right side? Okay, that means one of the things we can think of it like this. So what is the sort of like, let's say, probability of having that? Configuration 1, let's call that the one that we have, exactly half and half, compared to, for example, configuration 2, in which oxygen and nitrogen molecules are distributed uniformly throughout the room. Obviously, configuration 2 has higher uncertainty. Okay, one of the things we can talk about, like, let's say, where the oxygen molecules are, because configuration 1, which is this one over here, has a low uncertainty. If I can achieve this, then I can for sure know where the oxygen molecules are. They all, on the left side. I know where the nitrogen molecules are. They're on the right side. That means low uncertainty. When they're all distributed randomly, then I have high uncertainty, which means that I don't know where the molecules are. Could be left side, could be right side, could be somewhere in the middle, and things like that. Now, also higher probability, right, for you to have configuration 2, because if you're talking about, oxygen air molecules, right? So what is the probability of having configuration 1, where they're separate, compared to configuration 2? Well, configuration 2 is much more probable. Okay, it has a much higher probability. That means one of the things we can say here is that configuration 2 also has a higher entropy. That means entropy for configuration 2 is greater than entropy for configuration 1. Now, as you can see, right, for a system of dice and poker hands, comparisons between probabilities for various microstates involve relatively small numbers. And microstate of 4, for example, right, a pair of dice only has 3 times as probable as microstate of 2. That means that when you talk about, microstate of getting 4, you have 3 different ways of getting 4 compared to only one way getting 2. So it's, 3 times more, probable. But when you talk about microscopic thermodynamic system containing Avogadro number of molecules, ratio of probabilities can be pretty much astronomical. All right, so then here's an equation that we can use to calculate the entropy. So the numerical evaluation of entropy, where Kb is the Boltzmann constant and W is the number of microstates associated with the microstate. Probably the microstate over there. W represents the number of ways of achieving microstate. So microstates with larger number of microstates have a higher probability. For example, microstate of 4 has a higher probability than macrostate of 2, right? 3 times more probability. Okay, so that means macrostates with larger number of microstates have higher probability and equivalently higher entropy. That's why entropy of state 4 and microstate 4 is greater than entropy of microstate 2. Right, so units of entropy are then a Boltzmann constant joules per Kelvin. Okay, that means this is one of the ways we can basically represent entropy in terms of the this equation over here. Okay. Now, in terms of then entropy, right, energy spreading, you can see, right, we can relate entropy to energy spreading. Okay. So the natural tendency for energy to undergo spatial spreading in time. So that's why sometimes the entropy is known as arrow of time. So representing increase in entropy. That means as a function of time, you can assume that entropy only increases of the system. We can see that. So you can see, right, if basketball dropped onto a floor, it bounces several times and eventually it comes to rest. So initial gravitational potential energy in basketball earth system transformed to internal energy in ball and the floor. So energy spreads outward by heat into air, into regions of floor further from drop point. Okay, some energy spread throughout the room by sound.